All right, so this is just a quick video to go over our three disaccharides, lactose, sucrose, and maltose. Some of you already did the first two in class, so you can skip ahead a little bit in the video, but make sure you watch what you need to watch and continue through to the end, because I might add in some new stuff that you need to know. So to start out with this lactose, obviously you're going to need a little bit of time to draw what I have drawn already. Forget about this little oxygen down here, but you need these two rings and you need to number them appropriately because each one has 6 carbons in it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And again, you can pause, obviously, if you need to draw this and you don't want to miss out on anything. But I'm going to start and just jump right into this, right? My first sugar over here, this carbon, that number 1 carbon, is my anomeric carbon. It's that original carbon that would have had the aldehyde on it, right? So it's where it was my carbonyl carbon from last chapter. So I need to find that, because lactose in your notes said that it had a beta 1 to 4 glycosidic bond. And I need to understand what that means. I need to be able to draw one of those. I need to be able to identify one of those on a model that you'll see later, right? So beta 1 to 4, right? Again, beta means that in terms of this anomeric carbon and this carbon up here, the number 6 carbon that's hanging off of the ring, right? If it's beta, remember, my oxygen off the anomeric carbon should be on the same side of the ring as that carbon, the number 6 carbon that's hanging off the ring. So if I'm going to put this oxygen in between these two sugars to try and connect these sugars, I have to know if it's going to be down here and connected below or connected above. And in this case, since it's beta, it should be on the same side. If this carbon is up, then this oxygen needs to be up, and I need to connect it like this. So that's where my beta comes into play. And I'm talking about the number 1 carbon right now, right? This anomeric carbon right here. And my bond, my glycosidic bond, this oxygen is up relative to this carbon up here. It's on the same side as that carbon, the number 6 carbon. So that's what makes this a beta, right? Whereas this other side, right, where I'm connecting from this oxygen to the 4, that's where the 4 comes from in this picture. But that bond doesn't actually matter as much, whether it would be alpha or beta, because number 4 is not an anomeric carbon, right? The anomeric carbon on that sugar, that ring, is over here, and it's not even involved in my glycosidic bond. It's not involved in my acetyl. So I don't really care about that second ring, whether it's up or down, because there is no up or down for that situation, right? I'm just connected to that 4 carbon. So the beta applies to that 1 carbon because this oxygen is up and on the same side as this number 6 carbon, but otherwise the 4 can be connected however you want it to be. But this is how I would generally draw that lactose. Now, if you're looking at the models, you have to try and find, right, essentially these two oxygens that are connected by a carbon, and that's how you find the anomeric carbon in question, this carbon number 1, and that's how you can look on that ring, okay, is this oxygen up or down relative to this 6th carbon that's also on the ring? So you try and find that anomeric carbon first and foremost, because then you can know if this is lactose with a beta 1 to 4 bond, or possibly it could be that maltose from later that I'm going to draw here in a little bit that's actually an alpha 1 to 4. So that's my lactose picture. Sucrose is a little bit different, and you have to draw this in, and it looks a little funny because that second ring is upside down. Sucrose is actually the easiest one to identify because it's got 2 rings, but one of those rings isn't a 6-atom ring, right? So this one is just like before, 1, 2, 3, 4, 5, 6 carbons. But this 6-atom ring, or excuse me, this 5-atom ring over here is actually from a fructose, not a glucose. So it also has an extra carbon in here, so you're going to see that I'm numbering this a little funny. This is actually the 2, 3, 4, 5, and 6 carbons. So I haven't drawn the 1 carbon yet, but that's because I don't know where to put it yet. So sucrose has an alpha beta 1 to 2 glycosidic bond. So again, I'm just looking at the anomeric carbon for this first one. And again, it says alpha. So I should look at this carbon here that's up, and alpha means opposite of that carbon. So I need to put my oxygen, again, this little oxygen hanging out down here, I need to put it below the ring, right? So I'm going to have this bond headed downward from the number 1 carbon. So that's my alpha. That covers the alpha label and the 1. But the other part of this sucrose that makes it weird, my second ring, this 2 carbon, is actually also an anomeric carbon. Unlike on my lactose, where the other anomeric carbon is not involved in my glycosidic bond, this time the anomeric carbon is connected to that oxygen. It is involved in that anomeric bond, which is why there's a second label here that says beta, right? Now, again, I already did my alpha, I went down, and based on where my picture's at, it's kind of hard for me to do anything but connect back up here to this 2, right? That was kind of a terrible connection, so let me try that again. So I kind of have to go up to get to the 2. But what I need to recognize there is that in terms of the beta, right, this is my carbon that I'm comparing to. Remember, beta means same side. And since both of these bonds, this bond from the 2 carbon to the oxygen and this bond from the 5 to the 6 carbon are downward on my picture, those are both going to be on the same side of that ring, right? So again, I actually have 2 anomeric carbons involved in this. One's gonna, the one that's a number 1 carbon in the first ring has an alpha connection, so I have to go down because this is up. Whereas on the other side, since I came up, I have to come up from this carbon down here too. They have to be on the same side, those bonds. So I have an alpha beta 1 to 2 glycosidic bond. Again, when you look at the models, this one's going to be pretty easy to figure out which one is sucrose because it's the only one that has a 5-atom ring in it. So when you look at the fructose side of this ring over here, right, you already know which one it is. The thing that I'm missing on this picture right now, remember I needed another carbon. Since that glycosidic bond went down, I have to have my number 1 carbon come up relative to that number 2 carbon. So there are 2 carbons hanging off of that fructose side, and you'll see that in that model. But I didn't know where to put that carbon quite yet because I had to figure out where the oxygen goes first. Since the oxygen was beta, same side as the number 6 carbon, the 1 carbon has to be opposite of that 6. So then we got maltose. This is where everybody kind of needs to join in, and I can start labeling and figuring this one out. So this one again is 2 rings that both are glucose type rings. They're both purinoses. So 1, 2, 3, 4, 5, 6. Label both of them. This one shouldn't take as long because I've already kind of explained the process. But maltose is supposed to be a alpha 1 to 4. It has an alpha 1 to 4 glycosidic bond. So again, I find my 1 carbon here, and alpha relative to the 6 should be down. So I'll put the oxygen down here, and then I'll draw my connection, obviously, my bond between this one and that oxygen. I'm going to use black. And then I'm going to go to the 4 next, again, the 4 is not an anomeric carbon because the 1 is an anomeric carbon. We'll talk more about that later, how that affects this disaccharide. But since it's an alpha 1 to 4, again, alpha only applies to the one anomeric carbon that's involved in this glycosidic bond. The alpha is that 1 carbon that I circled. The 4 doesn't matter because it's not an anomeric carbon, so I don't have a label for that. I don't have a second label like the sucrose had. But maltose versus lactose, there is actually a pretty big difference, right? The next connection that we need to make, we need to understand lactose versus maltose. The only difference is a beta versus an alpha glycosidic bond, right, as far as our purposes are concerned right now. And we know that some people are lactose intolerant. So what makes that beta bond different, right? We should understand that lactose intolerant people have trouble breaking down that sugar. They have trouble breaking down that glycosidic bond. And that beta makes a difference in this picture. So when it's all said and done, it's really hard to visualize this without using a model. So it'd be most useful if you could, at some point, hold that lactose molecule that I made, that model that I made, in your hands and be able to look at that glycosidic bond and look at the relation of the oxygen and the carbon hanging off the ring, right? So in my picture here, I have 2 atoms, this 6 carbon hanging off the ring and this oxygen that I'm going to focus on. If you look at that model, those atoms are really close together, depending on the conformation of the ring in that sugar. So we'll talk about that a little bit more. Maybe I'll take a couple pictures to show you the difference. But essentially, with that carbon being really close to the oxygen, it can be really hard to break down this glycosidic bond, right? Without a special enzyme to help you do it, you might not be very good at it, which is why people are lactose intolerant, or at least some people, Whereas maltose, if I look at those same 2 atoms, this 6 carbon up here versus the oxygen down here, they're going to be a lot farther away from each other, and they're not going to hinder each other as much. So when you try and react and break down that glycosidic bond, it's way easier to do it. Right? There's a reason why we're learning about these alpha and beta bonds, right? Beta bonds are much, much more difficult to break down, right? There's not as much space, right? When I talk about, the overall shape of this molecule, right? There's a carbon and hydrogens on that carbon that get kind of in the way of breaking down this bond. So these are hard to break down. Again, I might need to show you a picture so I can kind of confirm that, but you can play around with the model a little bit too, right? Whereas that alpha bond, much, much easier to break down. Easy to break down. So again, there aren't many people that are maltose intolerant, although it's not necessarily a sugar that you can take constantly all the time anyway. You're much more likely to ingest the sucrose. But the sucrose also has an alpha bond when it comes to that 6-atom ring, and the 6-atom ring is where the problem comes into play. The 5-atom ring isn't nearly as much of an issue. So it doesn't matter that in sucrose there is a beta bond, because it's really this alpha one over here that's affecting the overall structure, whether it be easy to break it down or hard. So again, last little add-on here, we need to know that lactose versus maltose, beta versus alpha, it's much easier to break down an alpha bond than a beta bond. That's why we care about the direction to begin with. That's why we've been talking about it. There's a reason why people are lactose intolerant. So as long as you kind of get the gist of that, and as long as when you look at those models that you're sub has out on a table, right? They should just be laying where I left them. You can identify which one's which. Each one has a color tag on it so that you can actually tell me which one's lactose, which one's sucrose, which one's maltose. So I made a form that's on Classroom. Go check that out and label those things appropriately and answer the question that's in there. Otherwise, when you're done with this, you can go ahead and work on whatever you need to work on for the day, because there's nothing new that we can go through. So just go ahead and use your time quietly. As long as you're working on something productively, I'm cool with it.